In this video lecture, now we will see how micelle formation takes place in detail. Right? In the previous video lecture, we have discussed about multimolecular, macromolecular, and association colloids. And we know that associate colloids, and we know that associate colloids are micelles. Right? So micelles come under associate colloids. Right? So what are associate colloids? If you just recall, associated colloids, right? These are micelles. Associated colloids, if you recall, are formed by association or aggregation of ions, right? And multimolecular colloids are those colloids that are formed by aggregation of atoms or molecules. So this was the difference, right? Associated colloids, these are formed as a result of association of ions, right? An example of associated colloids are soaps and detergents, right? So example are soaps and detergents, right? Now to understand the formation of micelles, how exactly the formation of micelles takes place, we take the example of soaps, right? And we'll see how ions in soap will undergo association to form micelles, right? And we also know that one micelle consists of around 100 ions, right? So we'll see how these 100 ions associate to form micelles, right? So soaps, soaps are sodium salts of higher fatty acids, right? Higher fatty acids are stearic acid and palmitic acid, right? So stearic acid soaps are sodium salts of higher fatty acids, and let's take the chemical formula of sodium stearate. Sodium stearate is a soap. Sodium stearate, and the other example is sodium palmitate, is also soap, right? Sodium palmitate is made from palmitic acid, and which is a higher fatty acid, and sodium hydroxide, and this is formed from stearic acid and sodium hydroxide. So this is CH3, CH2, 16, then COO, Na. This Na is from sodium hydroxide, right? These are higher carboxylic acids. Stearic acid, palmitic acid are higher carboxylic acids, right? So when you add this soap, which is sodium stearate, in water, it will dissociate, right? In water, it will dissociate to form CH3, CH2 whole 16, COO minus. This is an anion plus sodium, right? So this is a anionic soap, right? This is an anion, so this is a anionic soap. Now what we will understand in this formation of ionic micelle, how these anions, right, will associate to form ionic micelles, right? And one thing, these associated colloids or micelles, associated colloids at low concentration will behave normally as strong electrolytes, right? When their concentration is increased above a certain level, right? That level we call as, we have done this also in previous lecture, we call this as critical micelle concentration, right? So above critical micelle concentration, these anions will start associating, right, to form ionic micelles. So formation of ionic micelles take place above concentration known as CMC, critical micelle concentration, and above temperature, Kraft temperature, denoted by TK, right? So formation, micelle formation takes place above CMC and TF. TK is your Kraft temperature, right? Because this thing is important to remember, that at low concentration these associated colloids or soaps will behave like strong electrolytes, simple strong electrolytes, but when you increase the concentration, right, of these of these soaps in water, then above a particular concentration known as critical Micelle concentration, these anions, right, these ions in soap will start aggregating or associating to form micelles, right. Now, in order to understand the micelle formation, we have to understand the structure of this anion, right, which is your, in this case, this is your stearate ion, right, this is stearate ion, right. Now, let's understand the structure of stearate ion. Just remember these two things, CMC and TK. This is important, right. So, let's draw the structure here. This is CH3. We have 16 CH2, 16 methylene group, 1 methyl group, right, CH2, 3, now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right, now this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? 16 CH2 group, then you have COO. This is your, let me just rub this. You can just take this down. I'll just rub this. Right. This is COO minus. So let's draw it the other way. We know that this is carboxylate ion, right? And one is bonded, one of the oxygen atom is bonded with a double bond, right? And the other oxygen atom is like this, bonded to this. So this is COO, right? This has a negative charge, right? Now, in order to understand this, right, we'll look this ion into two parts, right? One is your long hydrocarbon chain, which is this part, right? And we represent it as, we generally call it as R. This is your, R is your hydrocarbon chain, and this is your COO, right? This long hydrocarbon chain, this is your hydrophobic tail, right? We call it a hydrophobic tail. Why we call it hydrophobic? Let me first write, then I'll explain. This is a long hydrocarbon chain which is hydrophobic in nature. We'll just understand what is hydrophobic. And this is your head. Since this is in front, so this is your head, right? And this is your hydrophilic head. Hydrophilic head, right? Now let's understand what is hydrophobic and what is hydrophilic, right? If you remember, we have understood lyophilic and lyophobic, right? And when the dispersion medium, if you remember, is water, we call it as hydrophilic or hydrophobic, right? So here, hydro is water, phobic is hater, right? So water hater, that means this long hydrocarbon chain is water hater. That means it does not interact with water, and we know that hydrocarbons are insoluble in water, like alkanes, right? Alkenes, they are insoluble in water because they do not form ions in water. So we say they are water hating because they do not interact with water, because they do not contain ions, right? So this long hydrocarbon chain is your hydrophobic, means water hater, right? And this charged part, COO, charged part that has negative charge on it, this is your hydrophilic head. Hydrophilic is, hydro is water, philic is love, like lover. So this is philic is loving, right? Hydro is water, so water loving, that means this can interact with water, right? So this is your hydrophilic head, because hydrophilic, this head is your water loving, this, right? Water loving means this can interact with water, or this is soluble in water, we also call it, right? I'll repeat, this is your long hydrocarbon chain which is hydrophobic. Now hydrophobic is water hating, that means it will not interact with water, right? Since we know that alkanes are insoluble in water, so this is same as alkanes, right? It's a long hydrocarbon chain, so this is water insoluble, or it does not interact with water. And the head part, COO, which is hydrophilic, this is water loving, so this will interact with water, or it's soluble in water, right? This is what it means. So now the two parts of this molecule is clear, of this ion, I'm sorry, is clear, right? So now we'll see, when we dissolve sodium stearate in water, how will it interact with water, right? And one more thing, the molecules or ions that contain both hydrophilic and hydrophobic part, right, they are known as amphipathic molecules. Why amphipathic? Amphipathic, it's amphipathic, amphi is a Greek word which means both, right? Pathic is it means feeling, right? Both feelings, so it has both kind of ends, hydrophobic end and hydrophilic end, right? So these are amphipathic in nature. Amphipathic in nature means it has both hydrophilic and hydrophobic end, so these are amphipathic in nature. These kind of ions are amphipathic in nature. So now let's see, when you add this molecule in water, how will it interact, right? So when you add it in water, right, when you add it in water, say this is, you have water, right? So water, since I said that this hydrophobic end, right, is water hating, this is water insoluble, right? So when you add it in water, it will not interact with water, or it will interact with water to a very lesser extent, whereas this hydrophilic head, it will interact with water to a greater extent, right? Because it has charge on it, right? And we know that water also has positive and negative charge on it, right? So due to the presence of ions, this can easily interact with water, right? So when you add soap molecule in water, it will dissociate into stearate ions, right? And this stearate ions, right, in water, the hydrophobic tail of these stearate ions will keep itself away from water because it is water hating, and this hydrophilic head will interact with water because this is water loving, right? So this is how it will look like. Say this is the surface, right? This represents this long tail, right? So this tail will remain away from water, right? And this circle represents the head, right? It will go inside water. This is how it will behave, right? Right, this end, this is your long hydrocarbon chain, the tail part, and this is your hydrophilic head. So this is your stearate ion, and this circle is COO minus, and this is your, which stays away from water, is your CH3 CH2 whole 16. This is how it will behave when it is added to water, right? Now we said that at low concentration the Micelle formation doesn't take place because soap will behave as a strong electrolyte at low concentration. Now let's say what will happen when we increase the concentration of soap in water, that is if we add more if we add more soap to water, what will happen? When we add more soap to water, Then at higher concentration, when the concentration is above CMC, that is critical Micelle concentration, and temperature is above TK, which is Kraft temperature, right? When the temperature is above Kraft temperature and your concentration is above critical Micelle concentration, then these stearate ions would be pulled inside water, right? When these ions would be pulled inside water, they will interact with water. They will start interacting with one another. Okay, right? These ions will start interacting with one another. Right now, this is your water. Right? When the concentration is above CMC and temperature is TK, right? These ions, right, would be pulled inside the bulk of water, right? And then they will start interacting with one another, right? They will associate with one another, right, to form ionic micelle, right? And we know that one ionic micelle consists of around 100 ions, right? So it consists of 100 such ions, anions, right? So in water, inside the bulk of water, when these ions are pulled inside the bulk of water, these ions will arrange in the form of sphere, right, with the tail towards the center of sphere and these heads at the surface of sphere, right? This is how it will behave. This is how it will look like, right, inside the surface of water. So 100 such ions will interact, right, to form these spherical ionic micelles. Right, this is how the association of stearate ion takes place above CMC and TK, right? So at higher concentration, the RCOO or the stearate ions form an aggregate of spherical shape with their hydrocarbon chains pointing towards the center. This hydrocarbon chain is pointing towards the center and the hydrophilic head, right, is at the surface, right, pointing towards the center, and COO part outwards on the surface, right? This is your hydrophilic head. This is your hydrophilic head, COO minus, right? And this wavy line, right, which is the one represented by this wavy line, this is your CH3 CH2 whole 16, this part, right? So this is your ionic micelle, right? Stearate ions will associate to form this spherical shape ionic micelles inside water, right, with the long hydrocarbon tail pointing towards the center of the sphere and this COO part at the surface of sphere, right? This is how it will look like. So this is an ionic micelle. These ionic micelles consist of at least 100 ions. 100 such ions will associate to form these ionic micelles, right? So I hope this is clear to you, right? After this we will go through the cleansing action of soap, right? And to understand the cleansing action of soap, again we need to be good with the understanding of the structure of these stearate ions, right? Now we have, this is an example of anionic soap, right? This is, right, this molecule is an anionic soap. I said that detergents are also examples of associated colloids or ionic micelles, right? So sodium lauryl sulfate is a detergent, right? This is an anionic detergent which consists of 11 methylene group, right? Formula is CH3 CH2 O SO3 minus sodium lauryl sulfate, right? This is a detergent. this is a detergent, sodium, this has a positive charge, sodium lauryl sulfate, right? So these are anionic, this is an anionic detergent, right? This is an anion with it, and this is an example of anionic soap, right? So anionic detergents and anionic soap consist of these anions, right? Then these anions will interact in water above CMC and TK to form these spherical shaped ionic micelles, right? The formation of ionic micelles in case of these detergents would be similar, right? It will also behave similarly when added to water. There is one example of since this is an anion, then we might have we have an example of cetyl trimethyl ammonium bromide, right, which is an example of cationic micelle, right? The mechanism of ionic formation would be same in these cases, right? Cationic detergent, like there is one cationic detergent, this is an anionic detergent. Then there is one example of cationic detergent as well. The name of the detergent is cetyl trimethyl ammonium bromide, right? CH3 CH2 CH3 CH2 15, then trimethyl 3-methyl group, ammonium bromide. Ammonium is N plus Br minus, right? N plus Br minus. So this is cetyl trimethyl ammonium bromide. I'll write it over here for you. Cetyl trimethyl ammonium bromide, right? This is an example of cationic detergent, this is anionic detergent, right? And the mechanism of the formation of micelle would be similar, right, in both the cases, right? So just remember the formula of these detergents as well, and the most important part is the hydrophobic tail and the hydrophilic head. Since this is hydrophilic, this can interact with water, right? So this will go inside water. This is hydrophobic, this is water hating, so this will remain away from water. It will try to stay away from water because this is water hating, right? Then at higher concentration, all these ions would be pulled inside water where they associate or aggregate to form these ionic micelles. And one ion, and in this ionic micelle, this tail part is towards the center and this head part is at the surface, right? And one such ionic micelle consists of around 100 ions, right? I hope all this is clear to you. Thanks.